Good morning, students. This is chapter number 14, Semiconductor Electronics. And today's topic is types of semiconductor. Now, students, you know that as per the energy band theory, semiconductor have moderate forbidden energy gap between valence band and conduction band. Now, the elemental semiconductor is divided into two parts. Number one, intrinsic semiconductor, and number two, extrinsic semiconductor. Extrinsic semiconductor is further divided into two parts, P-type and N-type semiconductor. So first of all, we are taking intrinsic semiconductor. It is also called pure semiconductor. Now, this is a crystal made of germanium. Semiconductor materials having the atoms of tetravalence means each atom containing 4 electrons in outermost cell, and to gain stability these atoms try to form their octet. Now, each atom of germanium or silicon form 4 covalent bonds with neighboring 4 atoms and complete their octet. Now, at a low temperature, each atom completed its octet, means no electron is free. So, there is no electron in conduction band and all electrons are in the valence band, right? So, if there are no free electron, it means its conductivity is 0 at low temperature. So, there is no free electron, so it cannot conduct the electricity. But if this semiconductor placed in the room temperature, the few electrons having the high energy in valence band jumps into the conduction band. Now see, in this structure, if we provide the heat energy, this electron is coming out from the covalent. It means there is a vacancy in the covalent bond, and this vacancy in semiconductor is called hole. So for each electron there will be a vacancy in the covalent bond. So there are two types of charged particles. One is free electron and another is positive. Now the second electron also goes away from the bond, means becomes free. So this electron also jumps from valence band to conduction band. Now the hole can move in the crystal, but physically hole is nothing but the vacancy. Actually what happens, the electron moves from one covalent bond to another covalent. So the vacancy is created into another covalent bond. So physically hole is not moving, but due to movement of the electron, the hole is appearing to move in opposite direction. Now if we see this phenomena in the energy band theory, in the energy bands, so there are few electrons in the covalent bond. This is the first electron. In valence band, this is the first electron, this is second electron, this is third electron. The position of second electron was this and the third one having this one. Now first of all, the first electron goes away from the covalent bond. So we can see it in the energy bands. Now second electron also goes into the conduction band, means becomes free inside in the crystal, and the third one moves from one covalent bond to another. So for the few seconds, third electron becomes free and then again come to the covalent. It means in the intrinsic semiconductor or pure semiconductor, number of free electrons is equal to number of holes. But due to less number of free electrons and holes, the conductivity of intrinsic semiconductor is very small. So we cannot use this semiconductor commercially. Now if we increase its conductivity, we have to add the few impurity atoms in the intrinsic semiconductor. And adding the impurity atom in pure semiconductor is called doping. After the doping, the pure semiconductor converted into extrinsic semiconductor. Now see, the doping is the process of deliberate addition of very small amount of impurity in the intrinsic semiconductor. This is the very small amount of impurity. Now impurity can be trivalent or pentavalent, nothing else but trivalent impurity and pentavalent impurity must be doped in the pure semiconductor to get the extrinsic semiconductor, right? But the process of adding the impurity is called doping, right? Now doping should be in very small amount and it should be in ratio of 1:10 to the power 6. It means if there are 10 to the power 6 atoms of germanium, then one atom should be added to in it to produce the extrinsic semiconductor, right? Now there are few processes in which doping can be performed. Now method of doping. First method is heating the crystal in presence of dopant atom. We have to put the germanium or silicon with the dopant. Dopant means trivalent impurity or pentavalent impurity in the ratio 1:10 to the power 6. Now we have to heat up the system and convert it into the vapor, right? After coming in the state of vapor, we have to solidify the material. So dopant homogeneously added to the germanium or silicon. So we get the extrinsic semiconductor. Second process is adding impurity atom in the molten state of semiconductor. Now we have to put the semiconductor, means pure semiconductor, and dopant and give them the heat energy to convert these material into the molten state and then get it solidification. So we are adding the impurity atom to the semiconductor. And the third process is the bombarding semiconductor by the ion of impurity atom. We have to hit the semiconductor by the impurity atoms. So these are the methods of doping. In the process of doping, we can get the extrinsic semiconductor. Now extrinsic semiconductors are, or impure semiconductors are of two types. First one is N-type semiconductor. Now in this process, we have to add the pentavalent impurity to the pure semiconductor. Now see, in this crystal, the germanium atom is missing from the center and added the dopant pentavalent. For example, arsenic. Now, arsenic containing 5 electrons in its outermost shell. Now, arsenic forms 4 covalent bonds with a neighboring atom, but the 5th electron do not get any position in the bond, right? This electron, right? It means this electron is not in the valence band and in the conduction band, neither in the valence band nor in the conduction band. It means it is in between valence band and conduction band. Now, if we give the heat energy to the semiconductor, or we put this semiconductor in the room temperature, few electrons get away from the covalent bond, means jumps from valence band to conduction band. Now, in this crystal, number of free electrons will be greater than the number of holes. Means in N-type semiconductor, electrons are majority charge carriers and holes are minority charge carriers, right? Now we can see that for the each free electron there is a hole, but the additional electrons given by this dopant, that is called donor atom. In energy band diagram you can see there is a energy level just below the conduction band, which containing the electron of dopant, means the donor atom. So it is called donor energy level, right? Now the conductivity of the N-type semiconductor is greater than the intrinsic semiconductor, since the dopant is providing the additional electron, right? So donor energy level contains all electrons of donor atom. Now P-type semiconductor. In this semiconductor, the pure semiconductor is doped by the trivalent impurity. Now see, in this crystal structure, this is the germanium crystal, and at the center there is a trivalent impurity. For example, indium. Now indium carrying 3 electrons in its outermost shell. It forms 4 covalent bonds with neighboring germanium atoms. But in the 4th covalent bond, there is a vacancy, that is called hole. It means at low temperature, its conductivity is due to this hole, right? Now, if we supply the heat energy, few electrons come out from the covalent bond, and so the number of holes are greater than number of free electrons inside the P-type semiconductor. So holes are called majority charge carrier and electrons are minority charge carrier in P-type semiconductor. Now at low temperature, there are all electrons are in valence band, none in conduction band, but the hole are existing just above the valence band, it containing all holes of trivalent dopant. So it is called acceptor energy level, since the dopant is acceptor atom. It wants 1 electron to complete its octet. So it is called acceptor atom, right? The P-type semiconductor contains electrons and holes, but the number of holes is greater than number of electrons. So this is the P-type semiconductor, right? Now we can distinguish the 2 type of semiconductor, intrinsic and extrinsic semiconductor, like this. Intrinsic semiconductor contains the elements having tetravalency. Its conductivity is very low. Its conductivity increases with increasing the temperature. The number of holes is equal to number of electrons. In extrinsic semiconductor, there is a doping of trivalent or pentavalent impurity. Conductivity is increased. Conductivity depends on the amount of impurity atom. and there is